Hello, everybody. Hope you're doing well. In this video, we're going to be talking about reinforced concrete once again. But in this video, we're going to be talking about moment resistance, which is one of our first big subjects inside of this course. And if you want to hop straight into the problem, you can click on the timestamp below. But if you want to stick around and listen to me talk for a couple minutes, you can find out what the crucial fundamental parameters are for solving moment problems like this, and also understand the theory behind these problems as well. So to take a better understanding of moment resistance problems for concrete beams, we need to look a little bit closer at the theory. And to do that, I wanted to just take this cross section and go over to this slide right here, which is just a breakdown of the main important points or the design assumptions that we take when we're designing a reinforced concrete beam. Now, the first parameter or the first design assumption is that the plane section will remain plane under flexural loading. Now, all this means is that the strain developed in our section is going to vary linearly from that 0 point at our neutral axis. We know that that neutral point is the transition point from compressive to tensile regions inside of our member. So from that point, we can see that we increase linearly up and up and up all the way to that top or max strain in either our concrete or our steel. But in this case, we would have a max strain in our concrete. We've already talked about the max strain being 0.035 in previous videos, but all you need to know for now is that that strain is going to vary linearly from the neutral axis. Now, why could this be useful? This could be useful because we can actually interpolate where the strain is going to be at any point in our section based on that limiting design parameter for the compressive strength of our concrete. But we'll look more into that in future videos. But for now, just understand that you're going to vary linearly from that neutral axis. Number two is strain compatibility. This is another one that ties into this plane section assumption. Pretty much all it states is that we have reinforcement and we have concrete inside of our beam. That's two different materials, right? There's going to be a bond between this reinforcement and this concrete, but the assumption is that at this bond location, the bond is going to be perfect. And the strain variation is also going to be linear as it passes through these two mediums of material. All this does is it ensures that this first point is still applicable for our design problems. Now, this third section, or all three of these points altogether, are the fundamentals to understanding how these concrete design problems are done in the first place. And the code references are here if you want to check them out. But the assumptions are we have a stress block that we're going to be using to solve for the compressive zone in our concrete member. Another important point is when we have a reinforced member, we're going to be neglecting the influence of the tensile strength of the concrete, because we've discussed in previous videos that the concrete is not very good in tension. So we just neglect it altogether and look at the strength of the steel for our tensile resistance. And obviously, this last point, which is just a design parameter, the max strain in our concrete is going to be limited. So we're going to limit it to 0.0035 for our problems. Now, the best way to explain this whole stress block theory is to start with some material properties. And we're going to be looking at the stress strain curves for steel and for concrete. Now, these black lines are going to represent the actual stress strain curves in the steel here, which will have a max yield strength of Fy. And then for concrete, we have this black curve as well, which is parabolic compared to the steel. And that's going to be limited by the specified compressive strength, which is Fc prime. Now, for limit state design problems, which is how we solve concrete problems, the theory and the method behind it, we apply factors. And this factor is called phi s for steel and phi c for concrete. And pretty much all this does is it is a factor that we apply to account for the material variation and uncertainty when in design. So for example, we know that steel has a fairly uniform and consistent manufacturing process when it's sent out to the field. You know, it doesn't have a mixed design that concrete would have, or a placing method where you're pouring, compacting, consolidating. There's a lot of other parameters at play when considering the strength of concrete. So we apply a factor that is lower than that compared to steel. But the main takeaway here is that we apply these factors in order to account for the uncertainty in the material once it is placed into our member. Now, looking a little bit closer at the stress strain profile for the concrete, we can actually notice something because we transfer this factored curve over to our block in our problem here. So this stress strain profile is actually representing the exact stress strain profile for our concrete member as well about that neutral axis because we assumed that the strain is linear. So we can directly take this graph of the stress strain where the strain is increasing linearly and transfer it right to our problem. But there's a problem here as well. We actually have an issue where we have a parabolic shape for this stress strain distribution. And engineers know that anything with a curve is typically hard to calculate for without using things like integration and other methods to solve. So lazy engineers have developed ways in order to make this simpler on ourselves, and that's creating a compression block or stress block assumption. And all that assumption does is takes this parabolic curve and transforms it into a rectangular block so that we can solve for design variables. And one of the important variables for this block is going to be this A value. And this A value is going to be the depth of this compression block with respect to the top compressive fiber. And this is slightly less than the C value, which is the depth from the top compressive fiber to your neutral axis. Why is that important? This is going to be important because we need to figure out what distance away that resultant compressive force is from our top compressive fiber. Now, how do we get it into a block? How do we go from this to this? Pretty much we are applying factors that equate this resultant force to this resultant force. And those factors are called alpha and beta, and they use two different numerical formulas. They're strictly numerical, just so that we can get this rectangular block into this shape. So all we're doing is plugging in FC prime, which is our design parameter for alpha and beta, and simply solving for those values. Simple as that. Now, the main takeaway here should be that we now have a compressive resultant force that can be easily solved for because we know this A value and we know the magnitude of this block. So we understand that stress is equal to force over area. So force is equal to stress times the area. So we can actually derive this formula here for CR, which is your compressive resultant force in that area. Similarly, you can do the same for your TR, which is your resistance in steel, and that's going to be phi S times Fy times As. And once again, for equilibrium's sake, if we have one force here and another here, for equilibrium to be satisfied, these forces have to be equal. So CR is equal to TR, which then allows us to rearrange those equations to solve for A, which is that important variable that we were talking about earlier, which is the depth of our compressive block. Now, why is this important? This is important because to get the moment resistance, you need to use that design parameter A. Why do you need to use it? Because we have a couple moment here between CR and TR. And we know that for a couple moment, the moment will equal to the force times the distance between the two. So the moment resistance will simply equal to TR, which is this set of variables here, times the distance, which is the depth to your reinforcement minus A over 2, which is half the size of the rectangular block. And that's really all there is to it. Now we can see what these parameters are doing when we actually hop into our problem that we were talking about earlier. Alrighty, so now that we've talked about all these design parameters, we can finally hop into the problem. and solve for this moment resistance. So the problem goes as follows. We have a properly reinforced beam with two 25 M bars at the bottom in our tension zone, and it gives us some parameters. It gives us the compressive strength, yield strength, material resistance factor for concrete and steel, and it wants us to solve for the moment resistance. Now, I just want to point out quickly that this problem says that it's properly reinforced. We're going to talk about this in future videos, but for now, all you need to know is that properly reinforced means that your yield strength for steel, which is given as 400 MPa, is going to be the design variable used in our problems because we have the steel yielding in our section. But this seems obvious, right? We have this as a design parameter, so why would it change? It could change because the section could be over reinforced with steel or under reinforced with steel. And if you're over reinforced, that means the steel might not necessarily yield. Therefore, we cannot use this Fy value in those problems, which is why I have Fs here. Fs is a parameter that we solve for if we are over reinforced, but we'll talk about that in future problems. For now, all you need to know is that our steel is yielding, so we can use this Fy value. Now let's talk about design procedure. We have these formulas here. We just need to solve for the parameters that we do not know. So the first one's going to be AS. We have the area of steel. We know that we have two 25M bars. Each bar is 500 mil. So we're simply going to have 2 times 500 for that AS, which is going to end up giving us 1,000 millimeters squared. Now, the second part of this problem would be normally to solve for D, but that's given to us. And we are also given that Fy is the design variable that we're going to use in our problems. So we can move straight along to solving for what TR is. And we know that TR from our theory is just this section of the formula right here. So TR is going to equal to phi S Fy AS. And simply solving for this, we have 0.85 times the yield strength, and that's Newton millimeter squared for MPa. And we have the area of steel, which we just solved for, and that's millimeter squared. All of this cancels out and gives us a value of 340 times 10 to the 3 newtons. Now we can go ahead and start solving for this A value. We have A is equal to this whole section on top. So we have 340 times 10 to the 3 newtons on top. And then on the bottom of our equation, we have alpha 1, phi c, fc prime, and b. The one we don't have is alpha 1, and I'll quickly solve for it here. It's just using this formula up top, as we discussed, and this is simply a numerical value that we use for the block assumption. And typically, this value is around 0.8. And solving here, we have it equal to 0.81. But for the sake of this problem, I'm just going to take it as 0.8. And normally 0.8 is a fine value to use if you have an FC prime between 25 to 40 MPa. And I'm going to go ahead and use that assumption as well here. So if we plug that in, we have 0.8 times 0.65 times the FC prime, which is 25 Newton millimeter squared, and the B, which is given as well for our cross section, which is 400 millimeters. That millimeter is going to cancel out. The squared is going to cancel out. The newtons are going to cancel out, and this millimeter is going to come to the top, meaning that our A value is going to be approximately 65 millimeters. And just like that, we have all of our variables in order to solve for this MR. So we're simply plugging into this formula. We know that this section simply represents TR. So that's going to be 340 times 10 to the 3, and that's going to be newtons. And then D minus A over 2. So our D value given in the problem is 450, subtracting A over 2, which is 65 over 2. And that's in millimeters. Solving for that, you're left with 141.9 times 10 to the 6 Newton millimeter, which in kilonewtons is 142 approximately kilonewtons per meter, which is typical unit convention for these moment resistant problems. All right, so that's it. That's the theory. That's the basics of moment resistant problems for concrete beams. And I hope this helped. In future videos, we're going to be talking a little bit more about more complex problems and what happens when we have over reinforced versus under reinforced beams. So stick around. Hope this helped. And thanks for watching.